Why does hot air rise? This is a hot air balloon. I remember as a kid just being really puzzled by that. Because our experience with like helium balloons, it's regular latex balloons, you blow it up with air and you tie a knot in it, and it's kind of buoyant, but it's not going to float. And here's this balloon that's got a ginormous hole in the bottom, and it's just full of air, but it'll carry people high up into the air. How does that work, right? Well, there's also a really big burner here that heats the air. When you heat a gas, it causes the volume to increase if the pressure is the same. This balloon is open to the outside pressure. It's not increasing the pressure of the gas inside of the air, but it's increasing its volume. You take a sample of a gas and you increase the volume. Does that change its mass? No, it just changes the volume. So if the mass stays the same, but the volume gets bigger, the density decreases. So when you heat a gas, it becomes less dense. And just like wood floats on water because wood is less dense than water, a hot air floats in cooler air. It will rise because it's less dense. So generally, the air at the top of a room is going to be warmer than the air at the bottom of the room. This balloon will rise because it's got hot air in it, which has a lower density. So the volume of a gas increases with its temperature. You can graph that. Here's a volume of, I don't know, we're starting around 23 at almost zero. And as we increase the temperature of that sample, keeping the pressure constant but allowing the gas to expand, we see a nice linear relationship here. If we extrapolate, that means we're taking the relationship here and we're going beyond where the actual points are, extrapolating and seeing where does this cross zero. This predicts that the gas would have a zero volume at minus 273 degrees. So that temperature, minus 273 degrees, is called absolute zero. It's the theoretically lowest temperature that you could have. It's the temperature at which nothing is moving. The molecules, the atoms, are not even vibrating in position. There's no movement at all. This is useful because here we've got this nice linear relationship between volume and temperature, but the equation for this line is going to be y equals mx plus b. There's an intercept if we use Celsius, because on the Celsius scale, this is where zero is. We're going to have an intercept. Oops, didn't mean to do that. We're going to have an intercept of, 20 liters or something here. And that makes all the math very awkward. If the intercept is zero, then things become nicer. So based on this, a new temperature scale was developed called the Kelvin temperature scale. And it's based on this zero volume thing. So minus 273 degrees Celsius is equal to 0 K. It looks like OK, doesn't it? The stockroom tech told me a great joke. He says, do you know that you can cool your body to minus 273 degrees Celsius and still be okay? Okay. It's really bad chemist humor. I busted up. That's me. Okay. So a guy named Charles, J.A.C. Charles. So this is late 1700s, early 1800s. He was a mathematician and a physicist, but he was looking at the relationship between gases and volumes. A lot of the early scientists were not specifically one branch of science. They were just generally interested in stuff. And so they got their hands into lots of things. He looked at the relationship between volume and temperature. So we have what's called Charles' law. And to use Charles' law, we have to assume that the pressure is constant and the amount of gas is constant. Because if those are changing, then all bets are off. Well, not really, but you get in more variables. So we can say this: the volume of a gas and its Kelvin temperature are directly proportional. This doesn't work with Celsius. So volume is proportional to temperature, or V1 over T1 equals V2 over T2. If we use this relationship with degrees Celsius, is it possible to have something at 0 degrees Celsius? Sure. There's some lemonade here with ice in it. That's a 0 degrees Celsius. That's the melting point of ice. What if you were doing a gas problem and you put in 0 degrees Celsius there? It's undetermined. You can't divide by 0. There's a problem. What if you had a negative temperature? What if one of these temperatures was negative? In order for this equality to hold, then one of the volumes would have to be negative. Can you have negative volume? No. You have to use the Kelvin temperature scale for gases. It's one of the most common mistakes students make, is they use Celsius. It doesn't work for Celsius. Got to use Kelvin. So when the temperature of a gas sample in kelvins doubles, the volume doubles. Temperatures must be expressed in kelvins. Did you hear that? Temperatures must be expressed in kelvins. Really, really important. Because the equation of the line, y equals mx plus b. That's the general equation for a line. B is the intercept. Using the Kelvin temperature scale, b becomes 0. And then y equals mx. Y is proportional to x. Simplifies everything. So kinetic molecular theory explains this. Let's think about the gas particles. If we increase the temperature, what does that do to the speed of the molecules? It increases. They're moving faster. When gas particles move faster, they're going to collide with the walls more frequently and with greater force. That would increase the pressure, but we're making it such that the pressure is equal. The pressure is the same. We do that by putting it in a container that can expand without any resistance. So if they're banging around more frequently and harder, they're going to cause the container to expand. The volume expands. So you increase the temperature, you increase the volume. Does that make sense? You heat a balloon, it gets bigger. You make a balloon colder, it gets smaller. Look at that. This is something you could try at home. Blow up a balloon, just kind of medium size. Put it in hot water, it will grow. Take it out of that, put it in ice water, it will shrink. Repeat until you get bored. Doing problems. A sample of a gas has a volume of 2.80 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What was its initial temperature in kelvins and in Celsius? The thing about the temperatures with the gas laws, I have never actually seen a thermometer that read kelvins. Most of the time we don't use kelvins. It's important sometimes. The conversion between them is pretty simple, and so you'll almost always see the temperatures given in Celsius. You need to remember that the temperature has to be in kelvins. Okay, so let's do this one. So again, we're just going to follow that pattern. We're going to make a table. And we're going to fill it in with the numbers as we come to them. We're going to have row 1 and row 2. We're going to read through the problem again. Volume of 2.80 liters. So I'm going to write that in my table, 2.80 liters. That's a volume. I'm going to label that column. at an unknown temperature. Skip over that. That's not a number. We put it in ice water, 0 degrees Celsius. So something's happened now, right? It was 2.8 at unknown temperature. We've done something to it. Now we've got 0 degrees Celsius, and the volume decreased to this. The 0 and the 2.57 go together. You see that? So 0 as a temperature is going to go over here, and 2.57 is the volume associated with that temperature. If you want to put both of these in row 1 and put the 2.8 down there, that's fine. It doesn't matter. It'll end up the same. What's important is you get the correct things associated with each other. 2.57 liters and 0 degrees Celsius go together. Before you go any further, you look at the Celsius and say, but that needs to be in Kelvin. Fix it before you start calculating. So adding 273 gives us a temperature of 273 Kelvin. I'm going to have to extend my table. Any questions? So I've got a table, and I have 3 numbers and a blank. I need an equation. I need Charles' law. So Charles' law is not P. Charles' law is V1 over T1 equals V2 over T2. For those of you who are good at algebra, you can rearrange that and you'll have no trouble. For those of you who do not care for algebra, this equation has fractions, and those fractions are going to get you in trouble. We need to get rid of the fractions before we do any rearranging. So to get rid of the fractions, we do what's called cross-multiplying. So when you cross-multiply, you multiply the top of one side times the bottom of the other side, and then the bottom of the first side times the top of the other side. Seen that before, I hope. So let's cross-multiply so that we can get rid of the fractions and stay out of trouble. So V1 times T2 equals T1 times V2. You okay with that? Cross-multiplying. V1 times T2, that's one side, is equal to the bottom of this side times the top of that side. Now I can rearrange this. I am looking for this missing blank, T1. So I'm going to rearrange this equation to solve for T1. I'm going to do that by dividing both sides by V2, because I want those V2s to go away, so I have T1 equals stuff. T1 equals V1 T2 over V2. Just be really, really careful with those 1s and 2s. Got my rearranged equation. I'm going to plug my numbers in. Volume 1 is 2.80 liters. Temperature 2 is 273 Kelvin. Divided by volume 2, 2.57 liters. We see that the liters cancel out. 2.8 times 273 divided by 2.57, getting 297.43, and the unit would be Kelvins. Thinking about significant figures, this 0 degrees Celsius is kind of sloppy. We could assume that that's absolute. That's a little iffy. Let's go with using 3 sig figs because of these. So we would call that 297 Kelvin. That's the temperature in kelvins. Does it make sense? So we had the gas at 2.8 liters. The volume went down. Did the temperature go down or did the temperature go up? What would make the gas get smaller? Lots of things shrink when they get cold, right? So it got colder. So the original temperature must have been higher. This is higher than that, so that's a good sign. It also wants us to give the temperature in Celsius. So then we need to take our Kelvin temperature and add 273. Sorry, subtract 273 to get the Celsius temperature. So 297 minus 273. 24 degrees Celsius. Any questions? Gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters and is heated from 36 degrees Celsius to 155 degrees Celsius. What's the final volume of the gas in milliliters? Well, again, we're going to need a table to collect the numbers. So we have a volume of 88.2 milliliters. That's a volume. It says this is an initial volume. It's heated from 36 to 155. So the 88.2 goes with the 36. And the other temperature is 155. There is a certain amount of reading comprehension that is necessary to understand these problems. But if you qualified to take this class, you should be very qualified to do that. What's wrong with those temperatures? They're in Celsius. We need to convert them to Kelvin. So 36 plus 273 is 309 Kelvin, and 155 plus 273 is 428 Kelvin. And then the thing I'm looking for is V2. So in these sorts of problems, the temperature has to be in kelvins. Did I mention that? It has to be in kelvins. The units in the volume can be anything as long as they agree between volume 1 and volume 2. So here we have milliliters, then it's going to give us this answer in milliliters. So that's fine. Okay, so then we need our equation. V1 over T1 equals V2 over T2. We're solving for V2. Let's cross multiply. V1 T2 equals T1 V2. We're solving for V2. So I want to divide by T1 on both sides. So those cancel out. So some of you should show your work here, what you're doing. The minimum work that I would like you to show is write out the table and write the equation as you've rearranged it. V2 equals V1 T2 over T1. I want you to write this out. If you do this or not, I'm okay with that, but get this equation. This helps you to see what you're supposed to do, and then if you did it wrong, you can come back and figure out what happened. Volume 1, 88.2 milliliters. Temperature 2, 428 Kelvin. Temperature 1, 309 Kelvin. You see that the kelvins cancel out. The unit of my volume is going to be milliliters. 88.2 times 428 divided by 309. 122.16 milliliters. Because I'm looking at this volume and I'm seeing 3 sig figs. So 122 milliliters. You may look at these temperatures and say, well, that's 36 is only 2 significant figures. Yeah, but when you add 273 to it, it gets 3 sig figs, because that can happen with adding and subtracting. Any questions? So, did the change go in the correct direction? We took a gas at 36 and went to 155. We increased the temperature. What do we expect the volume to do? Increase. And this is bigger, so that's a good sign. So using the equations like this is not the only way to solve these problems, but it's the one that seems to work for most students. There's another way where you make ratios and you think about how it's going to change. If you think you might like that explanation or that approach, please talk to me and I'll show you how to do it. It's really cool if it makes sense to you.